So the goals here, the outcomes are to build on our sort of general idea of what equilibrium is, which is when the forward and reverse rates of a reversible reaction are equal to each other, and then the system becomes unchanging at the macroscopic level. And so the extent at which that occurs, whether you have 80% of your reactant that gets destroyed or 50% before you reach your equilibrium, those are defined quantitatively by these idea of equilibrium constants. And so we want to develop intuition for how to solve for these constants and then how to think about them once we have those constants. So equilibrium constants typically have the shorthand notation of capital K, which is a little confusing because we use a lowercase k for talking about rate constants. But an equilibrium constant is really just the concentration of the products and reactants for a system at equilibrium. That's what it tells us. And so let's start with a generic chemical reaction. It's reversible. A plus B proceeds to make C. So we can start to write up an equilibrium constant expression for this generic reaction. We'll have that as capital K, and lowercase c is sort of just a generic way to indicate that. Some people will also write this up as K sub EQ, like this. But you'll find in this class we'll have lots of different flavors of equilibrium constants, like Ka or Kb. They are all defined exactly the same. The little subscript just sort of relates to the flavor of the reaction, whether it's an acid or a base or a redox reaction, etc. So in the most generic sense possible, the equilibrium constant is really just defined as the concentrations of the products divided by the reactants, each raised to their respective coefficients to balance that net overall reaction. So if this is generically true, then let's write up a more specific one for the reaction A plus B goes to C plus, which should look something like this, where we have the products d raised to exponent d, c raised to exponent c over b and a. So the major rule in using equilibrium constants is that these are concentrations represented by moles per liter, the units are. When we're writing this up for a reaction, this is generic, but when we start to talk about specific things, we only want to include those species in the equilibrium constant expression that are in solution, not anything that's a pure substance. Something like, if you saw something like pure water, like this, or something similar, those are pure. Those don't have concentrations, so they're not relevant in finding what that equilibrium balance is going to be. So we don't include pure. So what does the equilibrium constant actually mean? So we have it written out in text here that it's the concentration of products and reactants for a system in equilibrium, and now we have it written out algebraically. What does this actually mean? Well, it's just a number, all right? It's just a constant. And it's a constant at a given set of conditions that defines when the reaction is going to stop, such that the rate of the forward is equal to the rate of the reverse. So in this case of A plus B makes C plus D, we could write this up, and let's just say that Kc is equal to 10. What that means is that if K is equal to 10, it means that at equilibrium, there's going to be 10 times more product than there is reactant. So it literally tells us the ratio of products to reactants once the system achieves equilibrium, where the forward and the reverse reaction are the same. Similar, we could think about, what if Kc is equal to, say, 0.0001? Well, that pretty intuitively tells us that, well, now we're going to have way more reactants left over at equilibrium than we do products. And so in that case, we could say for very small cases, the equilibrium favors reactants. It's going to lie this way. And when we have larger cases, the reaction equilibrium favors the products. If Kc here is equal to 1, then it means at equilibrium we have equal parts of the reactants and the products that are in complete balance. So let's take a quick look at the same example we started this with, which is the decomposition of N2O4 to make 2 of these NO2s. Pause the video, see if you can write up an equilibrium expression for K for this, and then I'll tell you what it is, and let's see if we can make some logical conclusions about what it means. So hopefully you came up with an expression that looks something like this. The easy thing to forget is to make sure you're raising the exponential power to that of whatever that balancing coefficient is here. So we get something like this. So experimentally, the actual value K, which is a constant, is 4.64 times 10 to the minus 3, and that is temperature dependent. So we need to state the temperature. So this is at room temp, 25C. What does this mean? So let's use the same intuition we just used. What's the size of this tell us about at equilibrium when the forward and reverse reactions are exactly the same rate? What does this tell us? What are we going to have most of in that solution? So I like to sometimes, when I'm first thinking about a reaction like this, I like to actually just make it so I divide this by 1. It's the same number, but when I'm looking at the ratio here, what that really is telling me is that at equilibrium, when the rate of forward and reverse reactions are balanced, they're exactly the same. That means for every 1 part of N2O4 that I have 4.64 times 10 to the minus 3 parts of this NO2. And so that's telling me the ratio at equilibrium is that there's roughly 1,000 times more of the reactant than there is the product. And so if we were to say or evaluate, is this reactant favored at equilibrium or product favored, we would draw the conclusion that this is heavily reactant favored because of the size of this thing. There's about 1,000 times more N2O4 at equilibrium than there is the NO2. That's what this is telling us. So this is a super powerful tool. It tells us that regardless of how much we start with, we could charge this system with, a little bit of N2O4 or tons of N2O4. No matter what, it's always going to proceed towards an equilibrium ratio that satisfies that. That's always going to be true. Always, regardless of what you start with. It may take a long time to get there, which is a question for kinetics, but eventually it will, and that is what we'll capture.